Hey everyone, welcome back. So we're moving on to the next question in your quiz. Right, one of the next questions in your quiz. It's question 10. Right, the idea of this question is that you have a multivariate normal distribution which has a variance matrix which isn't necessarily full rank, so you can't invert it. And you want to show that you actually can get a nice looking chi-square distribution if you use the pseudo-inverse distribution or pseudo-inverse matrix of your covariance. Right, and the degrees of freedom is directly related to the rank of your variance matrix. Right, so to use this fact, we'll kind of note the hint they give us. You can represent a normal variable as a linear sum of a bunch of IID standard normal variables. Right, such that the variance matrix of x is actually B transpose. Right, since it kind of tells us this fact, we know we're going to use it, right? So before we kind of use that, I'm going to note this following fact over here, right? This is very important in this question. It's the fact that the rank of this matrix over here is actually the same as the rank of the individual matrices because it's in a special form, right? The form is the fact that it's transposed times by itself, right? Right, this is just a linear algebra result. I don't think you need to prove this. Right, so we'll just be using that. So we'll firstly just kind of figure out what x transpose sigma plus x is. Right, we just kind of break things down, figure out what we need to focus on. Sigma plus b z z, right? Oh, oops. Now, we have more of this, right? So since we know sigma is equal to B transpose, right? And we already we want to kind of express everything in that type of form, so we kind of just put that in. Z. Now, at this point here, some of you guys may be thinking that we could use this SVD immediately over here, right? Because this is a transpose matrix and this is just a regular matrix. And in the middle you have I, which is the diagonal, right? So you just end up with over here, oh whoops, I didn't mean to rub all that out. So over here this would be equal to B transpose I plus B transpose, and that's just equal to B, right? And I plus in fact is just itself, right? Some of you guys might be thinking this, so it just ends up with this, right? This is actually wrong, and the reason being is because technically this isn't actually SVD, right? If you look at this B matrix, it's not necessarily what do you call it? Orthonormal, right? Not necessarily orthonormal because it's not even full rank necessarily, as the question says. So you can't. This isn't in SVD right now, right? So you can't just do that. So since we use SVD a lot, we'll be kind of using it somewhere else. In fact, we'll be using it on just B, right? So using SVD on B, so that equals to U M V transpose, where rank of M is actually equal to R because the rank of B is equal to R from the above statement. You can see there. Right, we'll be using this, and we just kind of sub everything in. So we have equals to Z bar U transpose V M, right? Because it's symmetric, it's fine. U transpose V, so V, oops, that's U. U M V transpose V M U transpose plus, and then you just write out what this thing U M V transpose Z. Oh, that should be red. Alright, just plug everything in right now. Right, and if you kind of focus on this thing over here, you can see this cancels out because it's a orthonormal matrix, and you actually end up with M squared in the middle, right? So you get U M squared M, oh oops, no, M U transpose, and this is in SVD form. right? Because you can look, this thing over here is orthonormal, both of them are orthonormal, and the middle matrix is diagonal, right? So you end up having transpose VM U transpose. You just swap the outer two and transpose them, and the middle thing you find the pseudo inverse of. Right, so U M V transpose, and then you just do Z. Right. Now, since M's are a diagonal matrix, the pseudo inverse of it, or any power of it, you can just kind of swap it around because, well, that's how diagonals work, right? Diagonal matrices work. And over here, you can see that U transpose, U also cancel out. So you actually just end up with Z transpose, V M, M plus M, V transpose, Z. Right, so you have these two parts. You need to figure them out. Now, since M and M transpose on the pseudo inverse of M are both diagonal matrices, you actually end up having the fact that these two things over here just kind of build up to IR0, 0, 0 because of the fact that M is rank of M is R, right? So the first R columns are the only non-zero columns, right? So we multiply them, they're the only things that give you a non-zero answer. And since this is pseudo inverse, right, it's just a reciprocal, right? You just multiply terms, it's just all equal to 1. Right, same thing over here. And so you actually end up with kind of a compressed, how should I say this? A slightly reduced orthonormal multiplication, kind of. So if I kind of represent it again, it will be kind of something like I R0, 0, 0, B transpose, Z. Alright, just write that again, 0. So only the first R columns are being included. But the thing is about orthonormal matrices, right, is that each of the columns are orthogonal to each other, and they are, normalized, right? So even if you only include the first R in each calculation, they'll pretty much just cancel out. So you just end up with kind of, essentially, you'll end up with just Z and this middle thing here. Z. Because if you imagine that this thing is I, right? Just pretend this middle thing over here was I. Pretend this whole thing was I, right? V transpose. You'll end up with just V transpose. And since V transpose V is equal to I, right? That's kind of definition of orthonormal. You can actually show that this is also equal to I as a result. Right, I'm not going to show that here, but you can see that's true. Now, if you kind of remove some of the columns or on both sides, you can see that doesn't influence kind of the bottom half of the calculation, right? So if you kind of just focus on the first R terms, right, you'll still get a column of a bunch of 1s, right? So that makes sense that the final answer here is just the first R diagonals are 1s. Everything else is 0 because of this middle matrix. Right. That's pretty much how you can justify that. Right. Oh, oops. Right, and that's how you get this. Right. Now we have this. This is pretty much, again, similar story. You can easily show that this is 1R to R of ZI squared, right? Where ZI normal 0, 1 IID. Oh, that's not right, because that's the assumption of what Z is in the initial question given. IID normal, right? And since they're IID normal, right, and they're standard normal, right? IID standard normal, and there's all of them. This is by definition chi squared R, right? You have a sum of a bunch of independent squared normals, right? Squared, as you can see here, and there's R of them, independent, standard normal, and that just means it follows a chi-squared R distribution. Right, so as you can see, the most important part of this question really was the algebra breaking down, right? Kind of just recognizing how to break down the matrices efficiently, I guess. Alright, the biggest thing, so as you can see, the fact that it's R here, comes down to the fact that of this thing up here, since the rank of the original matrix is R, and the original matrix is represented in this form, that means rank of B, so one of the matrices, is also R, and that meant that the SVD form had a diagonal with R leading columns. And the R leading columns eventually lead down to this matrix here, because the fact of every other column is just zeros, so there's only R terms involved. Right, so that's pretty much how you do this question. Right, the last part's straightforward because it's just standard normal and the definition of a chi-square distribution. Right, so that should be it.